This is Chapter 17, Section 3. We're going to combine Section 3 and Section 4 together in one PowerPoint. Talking about current and charge movement. Have we talked at all about electric potential energy?
Yes.
What about the force of the electric potential energy?
Yes.
What about electric fields? Yes. So now add electric current into that. A lot of times people just refer to it as current, which is the rate at which electric charges pass through a given area. They give you the symbols that go with this new equation. I equals delta Q over delta T. I is the symbol, it's a capital I, is the symbol for current. It is the symbol for current. If we look at the units that go with this, for current, we usually use, anybody know what the units are for current? That's frequency.
Volts per second.
No. We're getting closer though. It's the amp. Okay? Q is charge measured in what? Q is charge measured in what? We're currently studying this. What's it measured in?
What did you say?
What's it measured in?
Coulombs.
Coulombs. And time's measured in? Seconds.
I was right.
So coulombs per second is the same thing as an amp. The official word for amp is what? That's an abbreviation of what word?
Amperage.
Ampere. So A-M-P-E-R-E, ampere. So we just say amp. So that is coulombs per second.
Electric current is the net flow of electric charge carriers from one point to another. The charge carriers can be negative, positive, or a combination of the two. Which is the case is not a concern for most applications. For this reason, scientists have chosen to treat most electric currents as if they were entirely due to the movement of positive charges. This equivalent current is referred to as conventional current. For many applications, it is not important whether the negative charge carriers are moving in one direction or the positive charge carriers are moving in the opposite direction. In these cases, scientists treat electric current as if it were entirely due to the movement of positive charges. The conventional current is a current that has the same net movement of positive charge as the actual current. In the case of a current within a metal, the actual current is due entirely to the movement of negatively charged electrons. If the electrons, which are negatively charged, move from right to left, the conventional current is an equal amount of positive charge moving from left to right. In particle accelerators, currents can consist entirely of moving protons. In this case, the conventional current is the same as the actual current. In some gases and dissolved salts, current can be due to positive charges moving to the right and negative charges moving in the opposite direction. In this case, the conventional current would consist of positive charges of an amount equal to the total movement of charge, but all moving to the right.
Okay. We're going to go back to the beginning of this because it's already showed all of your charges that have moved.
Electric.
And we're going to start with this right here, and we're going to start filling in case you didn't get it. What color were all of the positive charges that they looked at? They were red. We'll go ahead and fill in these where they were originally. So if it's red, it's considered to be a positive charge. And what color were their negative charges? They were blue. And they were always on the opposite side. And we're going to cut basically these two in half and look at what's going on in the two different cases. In the first one, you're talking about motion of charge carriers themselves, and in the last one, you're talking about conventional current. And it was telling you the difference between the two. What about motion of charge carriers? What is that actually supposed to be representing? Do you remember what it said? The motion of the charge carriers here? What does that actually mean? What does it mean when it says motion of charge carriers? What's carrying charge? Look out across through there. What's actually carrying charge? Okay, so your positive or negative charges that are actually in motion. Positive or negative charges in motion. And we look at first case, second case, and third case. In the first case, do you remember what they were trying to represent that they called their first case?
Negative electron moving to the left.
Yeah, but do you know what it was in? Like what substance they were talking about? Okay, that is within a metal. Okay, within a metal. That's their first case. Second case was in particle accelerators. Do you know what a particle accelerator is? Do you remember us talking about particle accelerators in chemistry at all? Kinda. When we talked about splitting atoms, particle accelerators, they can take... they show a positive charge here, take alpha particles, protons, can even be neutrons too, and accelerate them at a very fast rate to hit another particle and try to split it into smaller pieces. So that's what they're calling particle accelerators. And then in the third case, notice you're dealing with plus and minus charges in that first one. You're talking about some gases or dissolved salts. What is a good definition of a salt? A salt. S-A-L-T. What? And, okay. So last year in chemistry when we talked about salts, it was a halogen, which is group 17 nonmetals, attached to a metal, typically a group 1 or group 2 metal. So a metal attached to a halogen gives you salt. So that means you have a positive charge from your metal, a negative charge from your non-metal, and then what happens with the two. So when you see first, second, and third case, those are the different scenarios you're talking about. So in the first one, we're looking, and it is showing us motion of charge carriers within a metal. What is actually moving within a metal? Electrons. Remember us talking about an electron C? Okay, within metals, your valence electrons can freely move. So the motion of the charge carriers, it's moving from what appears to be on the right side and goes to the left. If you're talking about in the second case, which is a particle accelerator, and they're showing you the positive charge there. Okay, all of these are positive charges. It goes from left to right, and then in the third case, you have a metal and a non-metal, or you've got positive and negative charges, and they're going to be moving in opposite directions. So that's talking about motion of charge carriers themselves, what actually carries your charge and in what direction are they moving. And then we get to conventional current. Did you catch what they said, what conventional current actually is? Like, what's a good definition for conventional current? Anybody get that?
You consider everything to be because of a positive charge.
Yes. This is your electric current due to positive charges. So your net movement based on positive charges alone. That's our conventional current. So when we look at this, if you're in a metal, it's basically your electrons are flowing one way and your protons are flowing a different way. So it's going to move to the right. In the second one, your particle accelerator, it's moving to the right. Again, think about a fast loop. Particle accelerators usually They make them big. They're in a circular type motion, and they're just going around and around because they're trying to build up speed. And then in the third case, both of them are going to be moving to the right. Conventional current. Talking about through gases or dissolved salts. Who's got a question on this part? Drift velocity is the net velocity of a charge carrier moving in an electric field. So if you're looking at drift velocity here, you have the electron. Why do you think it changes path so many times? Any ideas?
Other charges?
He says other charges. You say hitting something, so it could be hitting other charges. Okay, but notice it is always straight line motion, and it's going to bounce off in different directions. It says drift speeds are relatively small because of the many collisions that occur when an electron moves through a conductor. We know metals make really good conductors, and we just looked at how are metals made up? What's going on with your valence electrons? They're loose. They're freely moving. So you have lots of electrons that are already freely moving. You're trying to move electrons through that. It's going to hit other free-moving electrons. So your drift speeds are going to be small. Drift velocity itself, that's the V drift. What does the big E at the bottom stand for?
The field.
That's the electric field. Notice your electron is moving in the opposite direction of the electric field. Do you see that? And it says your drift velocity is the net velocity of a charge carrier moving in an electric field, so it doesn't matter how many different motions it takes. We're just saying from point A to point B, what's your velocity going to be? We just want the net, so you don't include every sidetrack that it takes to get from point A to point B.
It's like displacement.
Yep. Yep.
An electrostatic equilibrium. Its electrons move randomly, similar to the atoms or molecules of gas. But if a potential difference is applied across the conductor, a net electric field is created inside the conductor.
So if a potential difference is applied, the electric field is created. Make sure you write that down.
When a conductor is in electrostatic equilibrium, its electrons move randomly, similar to the atoms or molecules of gas. But if a potential difference is applied across the conductor, a net electric field is created inside the conductor. Due to this electric field, the electrons inside the conductor move. However, the individual electrons don't move in a straight line. Instead, they collide with the vibrating atoms of the conductor and move in a zigzag pattern. The average displacement of an electron divided by the time required for the displacement is called drift velocity. The drift velocity is the net velocity of a charge carrier moving in an electric field.
So some of the things you should have gotten from that, when the conductor is in electrostatic equilibrium, electrons move how? How do they move? Straight line? Randomly. And then you've got the equation there. Velocity for drift is distance over time. That's an equation you've seen over and over and over again. They're just applying it to drift velocity now of an electron instead of something like a car.
What was the first thing you said? Like when the conductor is in equilibrium?
What was the very first thing we said?
Potential difference creates an electric field.
Resistance. It's the opposition presented to electric current by a material or device. We're using a capital R for resistance. What have we been using a lowercase r for? Distance, radius, something that has a distance or length associated with it. So capital R is resistance. The unit that goes with resistance is the ohm. And you see it kind of looks like it's the omega symbol, kind of looks like a horseshoe, but that is measured in ohms, and then you've got that is potential difference divided by current. So if we look at our combination of units, you've got the ohm is equal to, what is the units for potential difference?
Volt over amp.
Well, for potential difference it is
Oh,
volts,
okay.
and then for current it is amps. So volts per amp are going to be the same thing as ohms. Any questions? Okay. Considering what is ohmic versus non-ohmic. For many materials, resistance is constant over a range of different potential differences. If they obey Ohm's law, they are considered to be ohmic. Ohm's law does not hold for all materials, so if it doesn't obey Ohm's law, it's considered non-ohmic. Resistance depends on several things. We're going to look at length, cross-sectional area, temperature, and material. We're going to look at all of those. Before we get to the video that we're going to look at if you were to graph this information. So looking at two different graphs. What's our symbol for current? I. And what about potential difference?
Delta V.
Delta V. And then we're going to look at current and potential difference again. You can have two different types of graphs that we're going to look at. You've got one that's going to be a straight line. You've got one that is not considered to be linear. Which of these do you think is considered to be ohmic material? Meaning it's going to obey Ohm's law. You're going to have a constant over which your range of potential differences are going to occur. The top one. So if you have a linear graph, whenever you look at current versus potential difference, and by the way, the slope of that one right there, if you look at slope, what's our definition of slope? Rise over run. What's on our rise axis?
Average, sorry.
So current, and then potential difference is there. If you were to change that up a little bit, we just had this equation. R is equal to delta V over I. And so this is flipped, right? So that's the same thing as 1 over R, or 1 divided by resistance. Or resistance, it's its inverse. That is considered to be ohmic material. And the one below, where you do not have a linear graph, so your potential differences are not staying constant, is considered to be non-ohmic. Considered to be non-ohmic. Any questions on those two? We'll go look at a video, and we're going to look at the 4 things that we're going to say resistance depends on.
The length of wire depends on several factors: its length, its cross-sectional area, the material it is made of, and the temperature of the wire. Long wires have more resistance than short wires. This is because the current must force its way through a longer path. Similarly, a wire will have more resistance if it is very narrow. The current must all push through a tight space in order to flow. Copper is among the very best conductors of electricity. Metals such as iron or aluminum are more difficult for current to flow in. Higher temperatures also cause high resistance. This is because the random vibrations of the metal atoms can disrupt the flow of current. Consequently, the very best wires to use for low resistance would be short, thick wires made of copper and kept at a low temperature.
So, looking back at this right here, you need to know any of these combinations, what factors are going to affect resistance. The length part, which do you want for the Do you want typically lower resistance or higher resistance? Lower resistance. If you want your electricity to flow, you want low resistance. So, shorter length, larger cross-sectional area, find a material that actually conducts electricity well. Is copper the best conductor of electricity that we have? I think we've talked about this, what metal is.
Silver.
It's silver. Okay? Gold is better than copper. Silver's even better, but again, it depends on price. And then temperature. Why is it that you don't want a high temperature? What did they say actually happens at a high temperature?
The vibration of the atoms interferes with the charges passing through.
That's right. Whenever you increase temperatures, atoms start moving around much faster. Okay? So you increase those random vibrations that are going on within, in this case, it's a solid, so the vibrations are going to be more. They're going to make it more difficult for your electrons to flow through there. So the drift velocity is going to be lower. Any questions on those? So they can be used to control the amount of current in a conductor. Salt water and perspiration lower the body's resistance. Lower the body's resistance. And then you've got the word there, potentiometers. They have variable resistance. It's just throwing in another definition for you. That is the end of section 3. We're going to move on to section 4 now. So again, this is section 4. 17.4. Batteries and generators supply energy to charge carriers. We have direct current and alternating current. Have y'all ever heard of direct current and alternating current?
Yes.
What's their abbreviation?
AC/DC.
AC/DC. Not the band. We're talking about electricity. Direct current, this is where charges move in a single direction. What example did we talk about just yesterday or the day before? And I said that's an example of current that can only move in one direction. Your batteries. Alternating current, also known as AC current, the direction of charge movement continually alternates. Where might you find AC current? The wall outlets. Electric power, another equation. So we've looked at, so far, we've looked at current, then we looked at resistance, and now we're looking at power. We use a capital P for power. It is current times your potential difference. What unit do you think we use for power? We use watts. Capital W for watts. Capital W for watts. What was the symbol or the unit that we used for current? The unit is amps. And what was the unit for potential difference? Volts. So amps times volts is going to be equal to watts. That's watts.
Electrical potential energy would take place in this circuit if it were closed. When the circuit is closed, charges move from one terminal of the battery to the light bulb. Ignoring very small losses in energy in the connecting wires, there is no change in potential energy in this part of the circuit. When the charges move through the filament of the bulb, they encounter high resistance. The charges lose electrical potential energy as they collide with the atoms of the filament. The electrical energy is converted into internal energy, and the temperature of the filament increases. When the charges reach the other terminal of the battery, their potential energy is 0. For the charges to move from the second terminal to the first, they have to gain energy. This is provided by the chemical energy of the battery. The process goes on continuously until the chemical energy of the battery is exhausted. The electric power of this circuit is the rate at which charges lose electrical potential energy. Numerically, this is equal to the current flowing through the circuit times the potential difference.
So, if you don't think that you understand that graph talking about location of charge and potential energy, make sure you write that down. Something that they talked about as far as what is happening to your energy as you go through this, you start off with electrical energy. What does that change into? Do you remember? Electrical energy. What type of energy does that transfer into?
Yes.
Not what?
Internal?
Internal?
Yeah.
And internal energy changes to do what? It heats up the filament, so you're going to increase your temperature there. So some type of thermal energy. Any questions on this? So we change up our power equation a little bit. They gave us power is equal to current times potential difference. That's also equal to I squared R, which is also equal to delta V squared divided by R. Electric companies measure energy consumed in kilowatt hours. Notice it's kilowatt here, but kilowatt hours. And electrical energy is transferred at high potential differences to minimize energy loss. So they transfer this energy at a high potential difference, that's your delta V, to minimize energy losses. On the next slide, they're going to relate kilowatt hours to joules and probably show you the conversion for that. We'll look at that then. But I want to concentrate for just a second on this P equals I squared R. P equals I squared R. It's called, when we talk in that last one about transferring at high potential differences to minimize energy losses, it's called I square R loss. So you take this and just add the word loss onto it. So this is what, whenever electric companies look at, they have all these electrical lines that are transferring electric energy everywhere. Power lines just going and going and going. And you want to make sure that you are losing as little energy as possible through those power lines. So they carry extremely high voltages. That's that potential difference. They carry extremely high voltages to try to minimize this I squared R loss that'll happen because of the really long distance. Huh?
It's like if you have a pipe, the pipe is a leak, what the leak is, and you're pumping a small amount of water through, and it's leaking out like half, and you just pump more water through, but it's like a quick
Charge for the amount of energy that a customer consumes during a specific period of time, usually about a month. The kilowatt hour is a unit commonly used by electric utilities to express that energy consumption. We can convert kilowatt hours directly to the more common energy unit of joules. We'll begin with 1 kilowatt hour. We convert kilowatts into watts by multiplying by 1,000 watts over 1 kilowatt. Next, we can convert hours into minutes by multiplying by 60 minutes over 1 hour. We convert minutes into seconds in a similar fashion, multiplying by 60 seconds over 1 minute. If we pause to take a look at our units, we see that we can eliminate kilowatts, hours, and minutes, which leaves us with units of watt, seconds. Performing the multiplication, we find that 1 kilowatt hour is equal to 3.6 times 10 to the 6th watt seconds. The definition of a watt is 1 joule per second. If we express the units in this way, we see that the watt second is the equivalent of a joule. Therefore, 1 kilowatt hour is equal to 3.6 times 10 to the 6th joules.
So, all of that is information that you know. If I asked you convert a kilowatt hour to joules, once you get to how many kilowatts or how many watts per second, then I would want you to be able to go to joules at that point. So a watt second is the same as?
Joule.
It's the same as joules. Okay, a watt second is the same as joules.